Let us now start the discussion on electron transfer. And electron transfer, as you will see, these kind of reactions are also dynamically influenced by the solvent. So for electron transfer reactions, the mechanism for electron transfer reaction, particularly involving these transition metal ions, was proposed by Henry Taube, and this kind of mechanism is known as inner sphere electron transfer. I'm just writing instead of electron, I'm writing E minus. Now, what is inner sphere electron transfer? So let us consider a classic example. Let's say this cobalt complex, cobalt chloride. 2+, and it reacts with chromium hexacycle complex to give rise to cobalt 1 water ammonia 5 2+ plus chromium chlorine H2O whole 5, this will be H2 whole 6, 2+. All right, so let us first figure out which one is the oxidant and which one is the reductant in this equation. So if you look at the cobalt complex first, now you see there is a 2+ charge, and so the chloride it's a negative ion, ammonia is a neutral ligand, so definitely the cobalt is in oxidation state of +3. Now for chromium, it is very straightforward because water is a neutral ligand, so chromium is in oxidation state of +2 in this complex. Now in the product, as you can see, cobalt, water and pentamine, so these are all neutral ligands, so cobalt is oxidation state +2, and for chromium complex, the chloride has -1 charge, so it is in +3 oxidation state. So as you can see, the cobalt is undergoing here +3 to +2, so it is reducing, and the chromium is undergoing an oxidation. And what is interesting here, which Taube noted, is that this role of this chloride ion. So as you can see, this chloride atom, as if it's in this reaction, is mediating the oxidation or reduction. And this chloride ion, where it is located at the first coordination sphere, because this is a ligand directly attached to the metal atom. Initially it was attached to the cobalt, and finally it is attached to the chromium. And then Taube said the electron transfer in this case, where actually we have a redox couple, and then the electron transfer is being mediated by this ligand, which is the chloride ligand, Cl-. So since it is a ligand which is actually a part of the inner coordination sphere, so this type of mechanism is known as inner sphere electron transfer. And there actually Taube hypothesized, and which was also found later experimentally correct, that some kind of complex or the intermediate complex is formed where you have the cobalt, and as you can see in the starting point, that cobalt I have 5 ammonia, in the end also cobalt I have 5 ammonia, and only thing is that one water molecule replaces one chlorine. So we can write it something like this. Similarly for the chromium also, as you can see that there are 6 water molecules and there are 1 chlorine and 5 water molecules. So basically you can think that this water molecule is basically replaced by the chloride ion, and you have a chromium, and the 5 water molecules are kind of intact, and then you have a chloride ion which is bridging this cobalt and the chromium centers. So this is called a mu bridging thing, because it's the chloride ion is basically connecting the 2 centers. So this kind of mu chloride complexes is an intermediate in this case, and as if what is being found here, what Henry Tobbe proposed is that this chloride atom, or this bridging chloride atom, is as if the electron transfer is mediated through this bridging complex, which is mediated by this chloride atom. So finally you will see this water molecule is here, it is being removed, as you can see, and again it is being added. So as if the reaction proceeded through this pathway. And this kind of electron transfer, again as the name suggests, it's a mechanism, it's obvious from the mechanism that it is mediated by the ligand, which is a part of the inner sphere. Now for this work, Henry Tobbe won the 1963 Nobel Prize in Chemistry. But since we talked about the inner sphere electron transfer, there should be something known as outer sphere, but the inner sphere is kind of intact. And the outer sphere, let us just take a very simple example, like say for example this iron oxidation or reduction. So iron from +3 oxidation state gets reduced to iron +2 oxidation state, and as you can see the ligand of the inner sphere is still intact. And this was basically this kind of reactions which were categorized as evident from this stoichiometry as the outer sphere electron transfer, because people thought that electron transfer is mediated as if some external thing which is residing not in the inner sphere but in the outer sphere, because the inner sphere is still intact, which is the 6 water molecules that forms the inner sphere. So in this case it's a 3+ complex. We just redraw it once again. And then finally we have a 2+ complex, and it's kind of a direct electron transfer, not mediated via a ligand. Now for this Rudy Marcus actually developed a theory which is very widely known as the Marcus theory, Rudolf Marcus. And this theory was developed in the age 1950s. Now this is the same Marcus who developed the RRKM theory, and there is a connection because this is also related to the transition state theory, because if you remember the Marcus theory, which we again did not discuss in its full glory, and because of this was very much out of scope for this course. Now we only showed what are the Marcus expression, but we emphasized that Marcus made a connection of the RRK model, which was based on the model that we have S uncoupled harmonic oscillators. So that model to he said basically it's connected, there is a connection with this harmonic oscillator model with the transition state model, and he successfully made that connection. So in the electron transfer theory also he basically borrowed the idea of transition state and the potential energies for potential energy surface that we'll see in a moment. So this was developed in 1950s onward, but for that Marcus got the Nobel Prize in 1992. It took long years because of some reason, and we'll discuss also what is the reason. Now suppose for any general electron transfer reaction, suppose I have a donor and I have an acceptor, and what happens is that first the donor and the acceptor comes close together and then they form a kind of complex. This is known as association complex. Association complex. Now once this association complex is formed, then there is an electron transfer from the donor to the acceptor. So then the donor gets a positive charge because of the electron loss, and the acceptor gets a negative charge because of the gain in electron, and then they get separated. So if the reaction the rate determining step is this step, that the formation of the association complex, then the entire thing is basically controlled how the reactants are coming closer together. So again, this will be something like diffusion mediated. The rate will be diffusion mediated. However, if this is the rate determining step, where actually the electron transfer from donor to acceptor is the rate determining step, then actually the question is how, depending on the free energies of the donor and the acceptor, the rate of the reaction will change, and that we are going to discuss. So we are assuming that this step is the rate determining step. You can actually write it all these steps as a reversible steps, in the sense that there could be association complex and they can fall apart. There could be electron transfer and there could be back electron transfer and all these things. So we are assuming this in this case that the rate determining step is the electron transfer step itself. Now let us think what are the free energies or the relative free energies for the donor and the acceptor. So we'll just draw a diagram and few notations for that. So again, the donor has some electronic energy. Let's say this is the donor electronic energy, and I am labeling my energy scale, which is shown here as the zero of energy, where actually the donor energy is minimum, and also this coordinate. Now this coordinate is the electron transfer coordinate. Now again, it could be a combination of many vibrational modes. So this coordinate is the electron transfer coordinate, and this coordinate may be a combination of many vibrational degrees of freedom or vibrational modes. It may not be a single coordinate, but those combinations we are showing it as if it's a linear combination of this vibrational coordinate, which gives you an effective one-dimensional reactive coordinate, which is the electron transfer coordinate. And again, where the donor electronic energies are minimum, I call that position as say 0. So that now the donor will of course have some vibrational motion with respect to the reorganization of the solvents around it, and I'm just assuming here that these vibrational motions are all harmonic, in the sense that I have a parabola. This is just like the intramolecular vibration. So this is basically the same thing applied to for the intermolecular vibrations, but the assumption is the same, that I have a harmonic motion there and also I have a harmonic motion here. So this is basically the donor parabola. So I'm just labeling it as D. Maybe we can use some other color just to make sure that we have sufficient distinguishing feature. So this is suppose the donor parabola. This drawing is not very good, so you can try drawing once again the donor parabola. So it will be something like this is better. And then we also have an acceptor parabola, which is something like this. So this is acceptor parabola and this is the donor parabola. Now again, where the acceptor energy is minimum, so that coordinate, let us call it as x double prime. So again, x is the electron transfer coordinate and E is the free energy. And also we see that at the point the donor and the acceptor potential energy surfaces, these are all one-dimensional potential energy surfaces with the harmonic approximation, and that intersection, let us call it as position x prime. And now we see that we have several things. So we have also an acceptor minima, which is somewhere here, and since we called the donor energy to be 0, let us say that the acceptor is stabilized by an amount which I'm calling is as this energy gap as delta G0. Now delta G0 is the free energy for the reaction donor to acceptor. Now the way I have drawn it, actually delta G0 is negative, so the gap or the absolute value of the gap is minus delta G0. And then again we will define one more quantity, that is how much energy you need for the donor to cross this donor acceptor cross point. So that is kind of the activation energy for this, and we'll since this is an activation energy, we'll use a similar notation. I will write it as delta G dagger notation. So we have delta G dagger and we have delta G0 already defined, And there is also one more interesting parameter, and that is if you think that if I just excite the donor vertically, and if you see that excitation of donor vertically means it is an electronic excitation again. So if I move it vertically, which means actually I'm thinking that the solvents are not reorganizing, meaning at this energy where I have when basically I draw a vertical line from the donor minimum to a point where actually it just crosses the acceptor parabola, then I see that point means actually this is some energy with respect to the donor. This is energy of the acceptor, but this energy is basically the acceptor's energy for the same solvent configuration for the donor minimum. So basically you can think, let me first draw this and label this energy. So this is this energy, and that is known as reorganization energy, or we'll call it as a lambda. So basically lambda tells it is the energy required for the acceptor to go to the same solvent and vibrational intramolecular as well as intermolecular degrees of freedom, so that to tuning of that freedom, so that it has the right configuration of the donor ground state geometry. So if we supply that much energy from the acceptor to the donor, then to the acceptor, then the acceptor will have some energy which has the same configuration as the donor has. And initially there are a lot of discussion. People are thinking that this reorganization energy, how it basically takes into part, how it basically takes part into this electron transfer rates. And people thought that if I vertically excite the donor and I basically reach the acceptor curve, then actually electron transfer will take place. But this is not true, because what we'll see that usually most of the electron transfer reactions are thermally activated, not electronically activated. But we'll still see that this reorganization energy, or the lambda, actually takes part into the dynamics. So basically this is the reaction free energy, or free energy of the reaction. So again, this free energy means actually this is reaction Gibbs free energy. Delta G dagger is nothing but the energy of activation, or again it's a free energy of activation. And lambda, one of the most important parameter, is known as solvent reorganization energy, or simply reorganization energy. Now we'll find a simple relation between these terms, and keeping in mind that the rate constant for electron transfer according to the Eyring equation, which is a transition state theory, is given by kBT by h into e to the power minus delta G dagger by RT. And if you remember, there was an equilibrium here between these, once we did all this interesting calculation. And then we showed when we talked about the thermodynamic interpretation of the activation transition state theory, then we actually arrived at a relation where actually we had this kind of relationship at this equation. Now this kBT by h again is coming from the Eyring equation, and this delta G dagger is the free energy of activation. So all we want is an expression for the delta G dagger with respect to the delta G0, and then we are done. So let us now try to figure out, these are all parabolas, so we can actually write the equation like the equation for parabola, as you know, that is y equal to x square. So actually it is y equal to ax square with some constant, but we have drawn it in such a way that everything is scaled to 1, meaning the constant is already absorbed within x. So then we can write all the energy equations will be something like y equal to x square. Now following, let us first follow the parabola for which is for say minus, let us just try to figure out what is first the reorganization energy, lambda. If you follow the acceptor parabola, so suppose let me just draw on this side. Suppose I have a parabola like this, and this is the center of the parabola. Suppose this is x0, and I'm asking this question, what is the value at say x1? So what I will do is that at the value this thing, suppose this is y, and this is basically y1, this is y2, so I can just write y1 minus y2 is nothing but if I just change the notation here as x2 and x1, so it is basically x2 minus x1 square. So in the same token, I'm writing that y1 minus y2 in this case is the lambda, so the reorganization energy lambda is nothing but, let me use some different color for the equations. So the reorganization energy in this case is nothing but x double prime minus x prime. So the again the lambda, the x prime here or the other coordinate, as you can see, is basically 0. So let me use the same notation as I'm following, x prime minus 0 double prime minus 0 squared. So this is nothing but x double prime squared. So similarly, if you this is following the acceptor parabola, similarly we can follow the donor parabola, and we can easily figure out that this delta G dagger is nothing but if you follow this thing, it will be x prime minus 0 square. So that is nothing but x prime square. So ideally for this reorganization energy, if we follow exactly the way I have drawn, it is basically the origin as x double prime, so it will be 0 minus x double prime square, but since we are squaring it, it is the same. Now we have already expression for lambda and delta G dagger. So then what we are left with is, now think about it, like what will be this gap. So delta G dagger plus this negative of this free energy change. So delta G dagger minus delta G0. So basically this energy gap now we are talking about. Now following again, we can actually use this for any to evaluate it. Since these are all parabolas, we can actually use it for any energies. Now you can easily see that this following the acceptor parabola, we can say that again you just follow this x2 minus x1 thing. So this is nothing but the value of the acceptor parabola here minus value of the acceptor parabola here. So all I have to take is that x prime minus x double prime square of that, and that I now can expand. So it will be nothing but x prime squared plus x double prime squared minus 2 times x into x prime into x double prime. Now we can actually substitute the values of x double prime and x prime squared. So x prime squared, I know that it is delta G dagger, and then what we have here is x double prime squared is nothing but the reorganization energy lambda, and then I also have the 2x prime, so that I can just write it as like this. It's not x prime, it is x prime and x double prime. So we can actually get a very simplified relation that we can see here, that this delta G dagger term cancels out. So what we have is that 2x prime x double prime, I'm just writing the expression for this term, is nothing but lambda plus delta G0, and then I can solve it for x prime. So x prime is nothing but lambda plus delta G0 divided by 2x double prime, and x double prime again is nothing but the square root of lambda, but we are just keeping it like that. And so x prime is all we want is this quantity delta G dagger, because remember that we are going to use the Eyring equation for this. So this equation, where actually I have delta G dagger. So the expression for delta G dagger, as we see here, is nothing but x prime square. So I have to take the square of this entire thing, which is lambda plus delta G0 squared divided by 4 x double prime squared. But I know that x double prime squared is nothing but the reorganization energy. So I have to write it as lambda plus delta G0 squared divided by 4 lambda. So we have already got an expression for delta G dagger. So the rate constant, or the expression for the rate constant, will be K is e to the power minus delta G dagger by RT, or if I am talking about not in terms of 1 mole, so I can use KBT relation also, but let us just use the RT expression with KBT by H prefactor. So this is nothing but KBT by H e to the power minus lambda plus delta G0 squared divided by 4 lambda. So this is the expression we get for Marcus theory. Now this is not a very rigorous derivation of Marcus theory. There has been few approximations that we make, and those are basically there is no tight coupling between these electronic states of the donor and the acceptor, and also this will hold if the donor and the acceptors are not too close with each other. So now we are going to see what are the consequences of the Marcus theory. Now everything, if I keep on increasing the delta G0, will how the rate constant behaves will depend on this interesting relationship between delta G0 and the lambda. Now suppose we will consider 4 different scenarios where we will be using this Marcus theory. Now what are these 4 different scenarios? Suppose actually I have high negative values for let's say, or slightly positive value for delta G0. Now what do you mean by that? So let us think that the parabolas look like something like this. So I was using a different color, so let me also stick to the same color. So situation number 1 is I have donor parabola like this, and then I have acceptor parabola which is situated like this, and then another situation where I have the donor like this and the acceptor is like this. So in these 2 cases what we see here is that this term, which is basically lambda plus delta G0, this term. So what is the sign of this term? Now lambda is always positive. Now if the way I have drawn here in the first figure as well as in the second figure is that this delta G0 is positive in the first figure, in the second figure it is slightly negative. So if it is slightly negative or positive, overall this term is greater than 0 for 1 and 2. So then what will happen if I increase the delta G0 in this case? So the reaction rate actually decrease because it's a highly negative number, as we can see. It will be 4 lambda into RT. So with respect, if I just plot the reaction rate with delta G0, we'll see that in this zone, if I have a relationship between this free energy and the reorganization energy, something like that, so that this term is always positive, then I'll have always e to the power minus negative. So the reaction rate is not very high. Now the reaction rate will become maximum when this lambda is perfectly balancing the delta G0. In that case, if I want to draw the parabola, it will be something like this. I have a donor parabola and I have the acceptor parabola right here. Now you can see this is the situation 3 where I have the maximum rate. So the reaction rate will be maximum, but you can think also in this way that this is basically the cross point is right at the bottom of the donor. So I have zero activation energy. This is very clear from this picture. So delta G dagger itself is zero. And or mathematically you say that the activation energy is nothing but the reorganization energy is nothing but equal to the negative of the free energy change in this reaction. And then if I move this parabola, so what I'm doing, I mean, in this drawing is that I have a donor parabola and I have an acceptor parabola. So as if I started the acceptor parabola here, and then I'm actually moving it down. So then if I move it further down, then I'll actually basically I'm increasing the delta G0 further, then I'll hit a very interesting situation where I'll have a situation like this, because I'm moving it down the red parabola. Now you see that in this case what will happen, the delta G0 actually is so high negative that the lambda, the reorganization energy, is much smaller, and the lambda plus delta G0 together is again negative, and then the e to the power this term will again become the negative, and then we'll have less activation energy. So in the fourth case is very interesting. Now what we see here is that the lambda plus delta G0 again will be very much positive, in the sense that in this case the delta G0 is highly negative. It's not slightly negative, and the positive, then actually we have the positive region of this Marcus theory, and then the reaction rate will again fall, because so we have the fourth situation here. Now let us consider the fourth and most interesting situation. So before going to that, let me actually write the conditions for all of them. So in the first case we had first and second case we had this, and for the third case we had lambda plus delta Z0 was actually 0. So we had maximum rate. And now we are considering another situation where basically we are moving the acceptor parabola much down, so that I have an crossing somewhere here. Now in this case delta G0 is very negative, and if it is very negative, lambda plus delta Z0, maybe I can write it here for case 4, lambda plus delta Z0 is negative here. And since we are considering actually square of that term, again that's a positive number, and then what we will have, again the reaction rate will fall as we increase the delta Z0. So if I plot actually delta Z0 versus the reaction rate, we'll have a very interesting plot. So this is delta G0, this is the reaction rate, and if delta G0 is small or negative or slightly negative, as we discussed, so the reaction rate will first increase, and then at a perfect positioning of the reorganization energy with respect to the delta Z0, we'll see a maximum reaction rate. But then again, if we keep on increasing the delta Z0, which means actually this is more and more positive or more and more negative, in either case we'll have the drop in the reaction rate. Now this region is basically known as a Marcus inverted region, and for a long time people found that when I am having this kind of situation, like the situation 1 and 2, where lambda plus delta Z0 is positive, meaning that delta G0 is slightly negative, or delta Z0 is positive, meaning this region, it was well known to people, but this region was a question, and we had to wait for nearly 30 years to find that actually there is a inverted region, that the reaction rate, it was contrary to the belief that if I decrease the free energy gap, so probably the reaction rate will increase. But what Marcus theory showed, no, actually the reaction rate will again fall in this region, not actually increase if I further decrease the free energy between the reactant and the products. And this is nicely explained in this way we derived the parabolas. And then this region was unknown until in 1986 or so, when Claus and co-workers found that yes, experimentally they verified that this inverted region in Marcus theory, that was explained in Marcus theory, or that was basically Marcus actually predicted this region, that inverted region exists, and they found it experimentally. And then in 1992 Marcus was given the Nobel Prize in Chemistry for this fantastic work. So let us summarize that what we discussed under this section. So we talked about the dynamic effect of solvents, and we first talked about solvation by polar solvents. And there we talked about that as what the polar solvent does is that what a polar solvent does to a solute is that it stabilizes its electronic energy states, but this stabilization happens over time. So what will happen here is that if we can collect the emission from each of these states as the system is stabilizing due to reorganization of the solvent, I'll get the fluorescence spectrum coming from the blue edge to green and to red edge, which is evolving over time. And that time evolution of the fluorescence spectrum directly correlates with the motion of the solvents around the solute molecule. So that we know talked about the dynamic Stokes shift or time resolved fluorescence Stokes shift measurements. And secondly, we talked about electron transfer. And under electron transfer, we talked about first the inner sphere electron transfer, when ligand, which is a part of the inner coordination sphere, can actually participate directly in the electron transfer reaction as if it is mediated by a ligand exchange. And by formation of a mu bridging complex, and as opposed to the outer sphere electron transfer, where actually the inner sphere is intact, but somehow this electron gets transferred through space, and that was described by Marcus theory, and where we saw that this Marcus theory shows very correctly actually accounts for the fine balance between the free energy and the reorganization energy. So long story short, this free energy between the reactant and the product, it doesn't always mean that if I have a smaller, and suppose what we are discussing so far is that whether the this free energy thing, or let's say I have a donor and then I acceptor, and then if the acceptor has a higher free energy, this was case 1, or slightly negative free energy, so this was case 2, and then I have a very high free energy, or where actually it is we can actually have the zero activation energy, and then very high, where actually again I will have a decrease in the reaction rate, and everything if here in this case we are plotting with respect to the free energy only. It's negative, it's then more negative, and it is more negative, something like that. And then the crucial factor here is not the free energy alone, but the lambda, the reorganization energy. And for all these plots, we said that the lambda is kind of constant in this case, and we just varied the free energy by varying the just vertically moving the acceptor parabola with respect to the donor parabola. And if we do that, then we figured out that at a perfect balancing condition, the reaction rate will be maximum when the reorganization energy perfectly basically counteracts the free energy of the reaction. However, if the free energy of the reaction is even more negative, you will not gain in the rate increasing the rate constant. Actually, the rate constant will drop, and that is successfully captured in Marcus theory. So we'll stop our discussion on the these reaction dynamics reaction dynamics in solution portion. So where we have covered a great deal of reactions starting from the diffusion limited reactions, and then we also talked about the reactions between ions, and then we talked about briefly the dynamic role of solvents. And again, one can ask how this is measured. We did not discuss again this dynamics, how this is measured. One thing we mentioned when we talked about the kinetic measurements is the TCSPC technique, and by TCSPC technique one can actually measure the simply by electronics how to basically get the fluorescence spectrum or construct the fluorescence spectrum at different time. From that you can actually calculate the solvation time correlation function. There are also sophisticated techniques like fluorescence subconversion and many other techniques that we did not discuss. And electron transfer, for example, you can study with say pump probe technique, where suppose after electron transfer you generate an acceptor species, and this acceptor species has a suppose a characteristic absorption. So you can initiate the electron transfer with some optical pulse or infrared pulse, and then you can actually watch how this acceptor band is increasing over time, and how this acceptor absorbance is increasing. And from that actually you can calculate the rates of the reaction, and you can actually infer, you can have a lot of insights regarding the dynamics. So we'll stop our discussion on this reaction dynamics in liquid phase here, and then we'll give you a summary of the course afterwards. Thank you.